Yes, everyone is back. Yeah, good morning. Thank you very much for coming back. Yesterday I wasn't yet able to put the slides of my first talk on the webpage because somehow our computer didn't let me connect with SSH, and now I installed a VPN, and with that I was able to. So they're now up. Where I stopped last time was we had started looking at some of the things GEP can do. There is something underlying which is called method selection. And method selection is an attempt to have the computer try to be a little bit more clever in how to do things. So there are different ways how one can represent groups. There are different things which might be known about groups. And the more you know about the group, the better often the method is which you can use in certain cases. And GEP tries to do this. This doesn't try to be anything like artificial intelligence or so. So don't interpret this as trying to do something like Prolog or so, trying to prove theorems. That's definitely not what we want to do. But what we want to do is that if some operation gets called, say, normal subgroups, there are different ways how it is implemented for different groups, and this can decide on what kinds of objects they are. Is it a group of permutations? Is it a group of matrices? Is it a group given by a PC presentation? Is it some very generic group where the only thing you have is a multiplication and an inversion? How things are stored. For example, for polynomials, there are different representations, and something could be stored in a sparse form, and so a different multiplication routine would need to be used. And also, what is known about an object. If you know that a group is finite, suddenly certain things become available for that group which otherwise are not. And so, for example, it could be GEP happens to know for your group that it is solvable and has order 1234 or whatever. And what method selection does is it tries to select the most specialized method, the one with most conditions, which still applies to the object, under the assumption that it is the best. And this will allow the computer to try to be somewhat intelligent in this choice. I will talk later in the last lecture, I will talk a little bit more about this, how one can look at it and how one can install one's own methods. But the important thing, even on a basic level, is that in some situations, it really can help GEP if you happen to know certain things. In particular, if you have a large permutation group to tell its size, to tell GEP how large it is, that can very substantially improve performance. And I mean, large means order somewhere 10 to the 30 and more. Yeah, later more about this. Okay, so to create groups, I've shown you already examples, but in general, there are basically three ways how you can get a group into GEP. The first is you can give the group by generators, by giving elements which can be multiplied and can be inverted, and the group is simply the group generated by these elements, the set of all finite products of these elements and their inverses. Permutations, matrices, automorphisms, and the group is the span of these generators. The second way to give groups is by a presentation. That's somehow analog in linear algebra. If you give a vector space, you can give a vector space by a spanning set, or you can give a vector space as null space of a matrix. And Heiko in his lectures already showed you some examples of presentations. His presentations actually are a special case. There are in GEP finitely presented groups for arbitrary permutations, and there are PC groups, which are groups using these particular presentations Heiko talked about, for which the performance is much better. The caveat here to keep in mind is if you make a new group, it is always different from all before. If you have a presentation and you create a group with that presentation twice, these groups are different. The elements of these groups are considered different and compare as unequal. That's a trap where one can otherwise fall into easily. The third possibility is there are built in some libraries. In some cases, it's basically functions for classes of groups, GL, symmetric group. And there are also libraries, certain libraries of groups of small order, transitive of small degrees, and so on. And these are typically represented in a suitable way. These are different ways which are suitable for the groups. So the small groups, most of them are represented as PC groups. Transitive groups of small degree are obviously represented as permutation groups and so on. And one can take these libraries and run through the libraries to look for examples. Yeah, what libraries are there? There is a library of small groups. These are groups of order up to 2000, oh, I should have said 2047, sorry. Excluding 1024. Why excluding this? Because the number here is so huge. Transitive permutation groups of degree up to 30, primitive permutation groups of degree up to 2499. These libraries both will soon be extended. Perfect groups and simple groups. The simple groups are a little bit different in that they are not that you don't parameterize them by order and number or degree and number, but you give them with a name. You want the simple group, which is called HS for the Higman-Sims group, say. For these first libraries, you would access them as, well, property would be small or transitive or primitive, say primitive group, and then parameters. Parameters could be, for example, with the primitive groups, number moved points, comma, 10, you want a group on 10 points. Primitive group, there would be the first parameter, there would be the degree, say 10, comma, and then a number, which is the number in the library, or small group, order 64, comma, number 15. And these libraries are guaranteeing that the numbering is stable, and this is a numbering also other systems use, so these numbers one can use in a paper and refer to them. There are also functions which search through groups, and they are, say, all small groups or one small group, and they get multi-parameters which are given in pairs, and if you can give arbitrarily many pairs, it's always property and the value you want for the properties. So all small groups, size 64 is, well, the mathematical solver, abelian invariance should be, I don't know, 222, and so forth, and you can give these parameters. Finally, for some generic constructors, abelian group or dihedral group, you can give the category as a first argument. So if you want the dihedral group by default, it will come as a PC group. If you want it as a permutation group, you can say dihedral group is perm group, comma, 8, and you will get that group of order 8 on 4 points as a permutation. Yeah, these different ways of representing groups are in part there because groups naturally arise in that way, but also in part because if you can go to a more specific way of representing it, suddenly more and better algorithms become available. In some cases, GAP actually will try to calculate internally another way of representing the group and work with that, but generically, one might have to do this by hand. But just looking at some ways of representing groups, so for example, we have permutation groups, they are not as efficient as polycyclic groups. The PC groups given by a PC presentation. Finitely presented groups behave, well, probably actually I should have moved them a little bit up, they're not as good as permutation groups. And in fact, finitely presented groups use permutation groups and use polycyclic groups. matrix groups currently also basically use the permutation representation, and generically, to do something with a group gap, computes a permutation representation if it doesn't know anything better just by acting on the elements on the right. And there is a mechanism called nice monomorphism, which I will talk about later, which does this translation automatically. But if you can give the group in different ways, the more down you can get on this scheme, the better your performance will be. How do you change this representation? If you have one representation and you want another one, there are a couple of commands which give you an isomorphism to that other representation. They're typically called isomorphism and then the kind of group you want. So if you have a group which is which in matrix grouping you want instead an isomorphic permutation group, you would call isomorphism perm group on that group, and gap will give you such an isomorphism. Isomorphism PC group will give you an isomorphism to a group given by a PC presentation, the group Psycho talked about. There is also isomorphism special PC group. Basically, in this case, a particularly nice PC presentation is used in which where you get fewer, where your collection process behaves better, and the arithmetic therefore is a bit faster. Also, what I should mention at this, that fits nicely in this place, if you want factor groups, the way to construct them is with natural homomorphism by normal subgroup. You will give a group and a normal subgroup. It will represent you get a homomorphism which has that normal subgroup as a kernel, and the image is the factor group, and it tries to represent this factor group in a suitable way such that arithmetic in this factor group is reasonably fast. So the image might be just some permutation group which happens to be isomorphic. The factor group is not represented formally by cosets. Yeah, since I started talking about homomorphisms, let me briefly summarize what can one do with homomorphisms. You can take, if you have an element, you can take the image of that element under the homomorphism. You can take the image of a subgroup under the homomorphism. There also is a function images representative, which sometimes is faster because it doesn't test whether this element actually is in the domain of the homomorphism. Vice versa, pre-images of a group that gives the full pre-image group, or pre-images representative of an element under a homomorphism gives you an element which under the homomorphism will map to this given image element. Kernel, since gap has not just group homomorphisms, but also ring homomorphisms and so on, the function is called a little bit longer. It's called kernel of multiplicative general mapping. Oh, I didn't talk about command line completion. What you can do in gap is always when you type in part of a command, you can type tab. And if there is a unique way to complete this, gap will do so. If not, it waits, and if you press tab a second time, it lists you all the ways how it can be complete. So that can save you typing such a horribly long name. So that's the kernel of the homomorphism, and then you can test it, whether a homomorphism is injective, surjective, and so on. Yeah, for creating homomorphisms, how can we create them? We can create them by actions, homomorphisms to the symmetric group by acting on a set, and I'll start talking about actions in a moment. Or you can give a homomorphism by specifying generators and their images. So you would have a homomorphism from the group from to the group to. Gens is a generating set for from, and you give images for gens under that homomorphism. This is the same idea as specifying a linear map by images of a basis. And this actually will test that indeed this mapping on the generators gives a homomorphism and return fail. Otherwise, there is an NC version for no check, which will be faster, but then obviously not do the test. Yeah. So that's some of the basic things you can do. Well, what does GEP actually do when you call these commands? We have elements. It's pretty obvious how we do arithmetic with the elements. Say if we have permutations, I guess you can all imagine how you're told to write a routine which multiplies permutations. But if we have a permutation on n points, we need roughly n times logarithm of n bits. Why that? Each point on which the permutation acts, we need log 2 of n bits to represent that point when we write down the permutation, and we have n points, so that gives us the number of bits. If we consider degree 10,000 and we consider a current laptop with 8 gigabytes of memory, we could fit in 40,000 elements. And then the memory is completely full to the brim. Well, we want to work with larger groups. So we cannot assume that we could write down all elements of it. What we want to do is, and what we need to do is to store only some elements and then represent a group by a generating set and some supporting data structure which might store some further elements. But essentially all the main thing which one needs to do internally, which GEP does, is it will try to just store a little bit of the group and try to do the computations with that. And what I will start looking at now is, in some cases, how this is done. And the reason I'm doing this is because that basically helps in understanding why the system behaves in certain ways, in the ways as it does. So, my second chapter is about orbits and stabilizers. And if you look at algorithms, basic algorithms which exist, which one can do, there are some things you know already, and there really isn't fundamentally that many paradigms of algorithms for algebraic computation. There is linear algebra, triangulizing matrices, inverting matrices, and so on. There is what I call combinatorial search, trying out all possibilities. That works. The computer is quite patient, but that is something which scales very badly if the problem gets bigger and is limited in scope. There is something which generically is called rewriting. This is basically replacing parts of a string by other parts. The collection process Heiko talked about yesterday falls in this category. And there is one thing which is specific to groups. That's group actions. And a lot of the group theoretic algorithms very deeply use the idea of group actions. So that's why I'm starting with these. Yeah, so let's assume we have a group G which acts on a set omega. From the right, I will describe the action with this. We have the obvious axioms for an action. And the basic theorem about group actions is that cosets of the point stabilizer correspond to points in the orbit. If we have the stabilizer of a point omega, the coset with representative G corresponds to the image of omega under G. We know the length of the orbit is the index of the stabilizer. Yeah, if we have a group action, there are a couple of things we can ask. We can ask, for example, give me the orbit of, I would like to have the orbit of a point. I would like to know how long is the orbit, what are the elements of the orbit. I might want to have the stabilizer of a point as a subgroup. And as a subgroup typically means I want generators for the subgroup. I don't want all elements of the subgroup. And the third problem would be a transporter problem. If I have 2 points in an orbit, give me actually an element which maps one point to the other. And in that category, for example, also false conjugacy test. We have a group acting on its elements by conjugacy. Give me a group element which conjugates one group element into another. These are the basic problems for orbits and stabilizers. how can we calculate an orbit? So let's assume we have the group acting on omega. The orbit consists of all images of the point omega under group elements. But I want to give the group only by generators. But every group element is a product of generators. Well, if the group is infinite, I also need to take inverses of the generators. For simplicity, let's assume the generator set I have includes already inverses of the generators. Well, so instead of forming all products and calculating the images of omega under all products, I can do this iteratively. So instead of calculating the image of omega under the product GH, I can take the image of omega under G first and then take the image of that under H. So I don't need to form all products of group elements. What I just need to do is I take the image of the point under all generators. And I take the elements I have then and take again images under all generators and so on. And I repeat that process. And if the orbit is finite, at some point, which it has to be if the group is finite, at some point this process must terminate. I will not get new images. And that's the basic idea of an orbit algorithm. So I have the group given by generators. I have the point. I start with a partial orbit which consists just of this point. I run through the partial orbit through all the generators, calculate the image of the point under the generator. If it's not in there, add it to the partial orbit, and I repeat that process until the partial orbit doesn't grow any longer. And that will give me, and at the end, when the partial orbit hasn't grown anymore, it must be the full orbit. That calculates the orbit. What is the cost of it? The cost of it is the length of the orbit times the number of generators is proportional to that, because I'm taking the image of every orbit element under every generator. Once I do the orbit, I can also find transporting elements by storing what is often called a transversal of transporting elements. I just keep track. If I get a new element in the orbit, I got it as image under some previous element in the orbit under some generator. So if I get the new element as image of some element under the generator H, and that element was obtained as image of omega under G, I know that G times H will map omega to this new image. So I can construct these generators, these transporting elements, simply by starting just taking the identity as transporting element for omega, and then every time I get a new point, I take the existing transporting element and multiply with the generator. And these transporting elements also would be representatives for the right cosets of the stabilizer because of the bijection between stabilizer cosets and elements in the orbit. So these products, a set of these products can be potentially large and could potentially need a lot of storage. So in the implementation, there are some tricks there that we actually don't multiply out this product, but we store it in some way as a formal product that is called a Schreier tree and saves on memory, but conceptually it's easier to just think about we multiply all these out. So we have also transporting elements, finally, for the stabilizer. And for that, we use what is called Schreier's lemma. Well, the basic idea is, let's suppose I have elements A, B, and C in a group where A maps omega to delta, B maps delta to gamma, and C maps omega directly to gamma. So with A, I go from omega to delta. With B, I go from delta to gamma. And I could instead have taken the step by C. Well, so I can take, if I go A times B and divide by C, what will happen? I will map omega to delta under A, to gamma under B, and C inverse will map the other way around. That will therefore map back to omega. So A times B divided by C lies in the stabilizer. And Schreier's lemma says that if I do this systematically in all possible ways for a given generating set, that set of elements will generate the stabilizer. So I need to take all transversal elements of the stabilizer, representatives for the cosets of the stabilizer, multiply them with all generators, and then divide off the canonical element for that coset. They will generate, these elements will generate the subgroup, and they are called the Schreier generators. So what does this mean for the stabilizer calculation? That's probably easier to understand than going through the details of that lemma. We start with a trivial subgroup as the stabilizer, and what we do whenever we calculate an image which is not new. So this is the case if it is new. If it is new, we do as before, we add a new element to the orbit. But if the image is not new, then we are in this situation. We have some element here, image under already an image. We take an image under the generator, but we knew already that we could get it this way. So in this case, we know A times B divided by C lies in the stabilizer. And in this case, A is the transversal element here, C is the transversal element here, and B is that generator. So we add that to the stabilizer and let the stabilizer grow. And by Schreier's lemma, this guarantees if we do this, all these elements together will generate the stabilizer. So we can calculate the orbit, we can calculate the stabilizer, we can find transporting elements. If we keep track of the transversal, we can write how the transversal elements were obtained as products and generators. We can basically write group elements as products and generators, and therefore work with homomorphisms given on generators. If we let a group act on its own elements by conjugation or on its subgroups, we can do centralizer, normalizer, but just in small groups because the orbit is worked out. If the groups get larger, more, this will not do alone, but more work is needed. So, how does group actions work in GAN? The basic operations are orbit, orbit of a point, orbits, or orbits domain. The difference is basically that orbits doesn't assume that the set of elements you give is closed under the action, but could just be seeds, orbit seeds, while orbits domain assumes it is closed and therefore is a little bit faster. Stabilizer, representative action, that's the transporter element. This is orbit stabilizer algorithm and sometimes backtrack, where I will talk about a bit later. Also, if we have a group acting on a set, we get naturally homomorphism into the symmetric group. That's action homomorphism. Or if you just care about the image, you could just call action. How are the parameters for these functions? Typically, the parameters are, first parameter is a group, which will act by its generators. Then a domain. If you just have the orbit of a point or the stabilizer, you don't need to give the domain, but giving the domain can improve the performance. And a point of which I want the image, or a list of point seeds for the orbits. And then, and why didn't I write this down? There is the last parameter, is a function which describes how I want to act on the objects, because sometimes there are multiple ways, or sometimes it's not clear to the computer how a group should act on elements. Let's look at this as some examples. So, and this is just a tiny, tiny example, so it fits on the slide. I construct the symmetric group on 4 points. I could ask for the orbit of the point 1 under the group. Well, because if the generating set 4 is chosen, 4 actually is obtained before the orbit is not automatically sorted. Doesn't have to be, just be aware of. I could take another, specify another action. Let's say I want sets of order 2 and I want to act on these sets by if you stay simply acting on the elements of the set individually, if I take the set 1, 2, I can calculate the orbit and I get these 6 images, right? 4 choose 2 is 6. These are the 6 images. I can ask for the stabilizer of one of these sets. I can ask for transporting elements. Representative action, if no transporting element exists, it returns fail. Another use where we use this special Boolean fail. Action homomorphism, that's the action of the group, the homomorphism into the symmetric group. This orbit was length 6, so this will be a homomorphism into the symmetric group of degree 6 by acting on these 6 elements. The image, of course, will still have order at most 24. And there is orbits. We would give a group here. In this case, I've taken the dihedral group of order 8 just to have something more interesting happening. Combinations, some of you, I told this routine already yesterday in the tutorial, in the practical session. Combinations is just the set of all possible 2-element subsets with points from 1 to 4. So this takes, constructs all these 6 subsets, and this group does not act transitively but has 2 orbits, one of them being basically corresponding to the diagonals of the square and one corresponding to the edges of the square. Yeah, so that's some examples of orbits. Stabilizer calculations. With action, I could take the action of G on this set, and I mentioned already I will get a group of degree 6 for action homomorphism we had. I could also have a group acting on its elements. Okay. Caveat, what we are doing here is if I don't specify something, the action is on points, that is the conjugation action. That's not the right regular action. The right regular action I get by on right, and we can see this by the fact that this action on the elements has multiple orbits. This action is not transitive. And while the action on right, in fact, it happens to be transitive. It has to be. When I calculate action, the points, the numbers correspond exactly to the numbers of the domain as given here. So if I had taken the elements of G in the list, I would know that the number 4 would correspond to the 4th element in the list, 16 to the 16th element in the list, and so on. Yeah, representative action on group elements, it's the conjugation action if I don't specify something before. And if I take conjugacy classes of subgroups and I take orbits of the representatives, I would in fact get a list of all subgroups of the group. Yeah, I mentioned already in some examples this action function as a further parameter. The action function is a function which describes how a group element will act on a point. It's a 2-argument function, and several of these functions are predefined by gap. There is on points, that's the action via the head operator, which is action of permutations on points, action of a group on itself, on its elements by conjugation. If you don't specify the action, on points is used. There is on tuples. Tuples are lists, and we simply act on lists by acting on all elements of the list and writing the images in the same ordering down. Sets does a similar thing but sorts it afterwards because we don't care about the positions. There is on sets, tuples, which are combinations of such objects. On right is right multiplication by the star operator. That would be, for example, action of a group on its elements by right multiplication, action of a group on cosets of a subgroup, action of a matrix group on vectors. If I want to act instead projectively, there is an action which is called on lines, and you can represent the projective space by picking only vectors whose first non-zero entry is 1. So on lines will act by right multiplication, but scale the vectors so the results so that the first non-zero entry is 1, and that will correspond to this projective action. There is, for action on subspaces, is this on subspaces by canonical basis. We represent a subspace as a list of basis vectors in reduced row echelon form, which is then a unique form to represent that subspace. Permuted would permute the entries in a list. And in particular, you can define your own function. So if we want a group of automorphisms acting on subgroups, we would, for example, take this function. Our point would be a subgroup, the acting element of homomorphism, and how shall it act by calculating the image. So that would give us a way to do such an image. And yeah, just some other example here. Action of the Mathieu group on sets of order 6. There is one surprisingly short orbit which corresponds to the coding theory constructions or design constructions for the Mathieu groups, which we heard about yesterday. In some cases, if you try to calculate certain things which don't work, Gep will do a little bit test. And if you get this error message, action not well defined, this basically means that some way this action doesn't work. For example, the identity element would not stabilize, the identity element of the group would not stabilize the point. In this case, it doesn't do because this orb of 2 is not yet a set. And we can verify that the Mathieu group indeed would be the stabilizer of this set of sets in the symmetrical. That's probably, let me skip that because that's a little bit technical. So let's look at this in an example. 2 by 2 by 2 Rubik's Cube. Why not the 3 by 3 by 3? Because it's a smaller example and it fits on the slide, and it also fits in memory for the computer. The way I describe, so I've taken the 2 by 2 by 2 cube and I've folded it just to describe how it looks like, and I've given numbers. What I do is, when rotating the slices of this cube, I could rotate the whole cube in space, and that's not considered solving it as a puzzle or making the problem harder. So what I actually will do is I will assume that the bottom right back corner, that's the corner 16, 19, 24, so that's 16, 19, and 24. This stone is fixed in space. That takes care of rotations in space, and therefore I have just 3 generators. I have a top rotation, a left rotation, a front rotation. So, if I do an orbit calculation, let's take the point 23. What is the orbit of this point under different elements? And I can build that transversal. So I would find, for example, that if I take 11 under the front rotation is 9, which also is in this list. So L cubed times F divided by L squared TL must lie in the stabilizer. And if I iterate this, I find elements which generate the stabilizer, similarly 2 or 3 point stabilizers. And if I actually look what these elements do and how they behave, I can see I get this way as Schreier generators relatively short words which do certain things on the cube. If you've ever looked at solution strategies for Rubik's Cube puzzle, what they do is they give you typically these kinds of images and say, in some kinds of combinations say, oh, if you do this operation, it will do these things, and these are useful things to do. How did they find them? Exactly as such Schreier generators. Well, so what we can do is we can ask Gep actually to use essentially an orbit algorithm to enumerate elements of the group and find ways to express them as words And for the 2 by 2 by 2 Rubik's Cube, this has 10 to the 7 elements. This all fits into memory. So we would construct the group from these 3 permutations. We make, because we want to represent it as a word, take a homomorphism from a free group to the cube, and I want to call the generators of the free group T, L, and F. And then I can ask for factorization of some element in the, some permutation in the group, and it would give me the word. This needs to store, well, 2 bits for every group element, so this will not work for arbitrary large groups. Instead of factorization, one could use more generically pre-images representative, which will work for much larger groups, but will first not be clever. T to the -3 would be better written as T, right? Because T to the 4 is the identity. If you rotate 4 times, you're back at the origin, and it will get words which generally are longer. Yeah, one can help the stabilizer calculation in some cases. For example, if we know the order of a stabilizer, this gives us early stop criteria. Maybe for time reasons, I'll skip this. So, but let's briefly look at this orbit stabilizer calculation. How well does it work? Well, we need to store the whole orbit in memory. That's a limitation. We need to store the transversal. I mentioned already we can store it in factored form, which is called a Schreier vector. There is some issue to construct a balanced tree to make the performance well. The cost of the algorithm is basically, if you try it out and you analyze it, it is dominated completely by the test whether a point lies in the orbit. That's completely dominating the runtime, and essentially one needs to use clever data structures for representing this orbit to make this test fast. The other problem is, if we look at the Schreier generators, well, Schreier's lemma says if you take all Schreier generators, you're guaranteed that they will generate the subgroup. And one can construct examples which basically, if you take a free group, you get examples which show that you can't generically leave any Schreier generator out. So the number of Schreier generators is huge. It's the index of the stabilizer, which is the length of the orbit, times the number of group generators. So if you have an orbit of length 1000 and a group, you have a group which is generated by 2 elements, completely harmless, orbit of length 1000, you get 2000 Schreier generators. You don't want to have a subgroup generated by 2000 elements for further working with it. Most likely 2 or 3 of them would be sufficient. A lot of them are redundant, a lot of them are trivial. So a big task is to reduce that number of Schreier generators. I mentioned data structures. There is a mechanism in GAP, a data type, which is called a dictionary, which will try to do clever things for storing an orbit, storing it, for example, as a sorted list when it can sort elements quickly, or even using hashing. And there is an operation sparse in key. If you want to ensure that your own objects can use hashing, you would need to install some method for sparse in key. Yeah, but the other problem is large number of Schreier generators. How can we reduce this? Well, if we have already a partial stabilizer and we can do a membership test in that partial stabilizer, we could initially test, is the new Schreier generator already contained in there? And if so, we discard it. That's still not guaranteed to produce a minimal generating set, but it will throw out a lot. On a very basic level, we could simply throw away the Schreier generators, which are the identity. The other thing which one can do is one can form what are called random subproducts. Let's not take all the Schreier generators, but let's take certain products. Let's collect a set of Schreier generators, and let's take some random subproducts. These are products of some of these elements in the given order. And one can show if one does this randomly, and there one can basically prove that with high probability, just few of these random subproducts would generate the subgroup with high probability, and this can be used to very strongly reduce the number of these generators, and these two ideas are used for working with permutation groups. So in the last this was now set to 50 minutes, right? This wasn't set for an hour, or was set to 50 minutes, so we have about 5 minutes left. Looking at permutation groups, which are an important class of groups. What does GEP do when working with a permutation group? The data structures it uses are building on orbits and the orbit stabilizer algorithm. So we have a group of permutations, degree, say up to a few million. Order of the group could easily be 10 to the 9. So orbits on elements are not doable. We want the order of the group. We want to be able to evaluate homomorphism. We might want to calculate subgroup centralizers, normalizers. We want to find something about the structure of the group, identify composition factors. How can one do this? And just as an example, here, this would be now the 3 by 3 by 3 Rubik's Cube. It's a group of order value. Count how many digits it has. And you can ask GEP, for example, to give you the composition series of the group. So, and this works quite quickly. So this will not enumerate all these elements. There is something else happening, and what is happening there, that's what I want to talk about. And the basic idea is to use subgroups. So, well, on an even lower level, the basic idea if you want to write an algorithm for doing certain things is if you can't solve the problem, you try to reduce it to a smaller problem. What are smaller things in group theory? Smaller things are subgroups. So, if we have a group we can't handle, can we reduce a problem by looking at a subgroup and the cosets? And because the order of the group is order of the subgroup times number of the cosets, this is basically logarithmizing the size of the problem. That's something very specific to groups. And that's why group theoretic algorithms work so well and have such a large scope, while if you try calculations in other structures, you often hit bottlenecks much sooner. Well, if we have a group of permutations, we have ready-made subgroups, namely point stabilizers. And why are they nice? Because their index can't be too large. If we're acting on a domain omega, the index of the point stabilizer of one point can be at most the size of omega. So if we have a group acting on 1,000 points, we know the point stabilizer will have at most index 1,000. It can't have index 20 million. And we can iterate this process. So U is now a subgroup. It's again a subgroup acting on omega. We can take now a stabilizer of another point, and so on, and get iterated a storage of about size omega to the log 2 of g. Why log 2 of g? Because if I have a chain of subgroups, at every step I must get smaller at least by a factor 2, so I can have at most log base 2 of the order of g many steps there. And this works for any kind of group and any action. It would work for matrix actions, a matrix group acting on vectors, automorphisms acting on group elements. The problem is, in many cases, the index of a point stabilizer is not small. The orbit length is too large. For example, if we would take GL and Q acting on vectors, we would get orbit length Q to the n, and that very quickly gets out of n. N or Q gets a little bit louder. But for permutation groups, this works well. And what I want to now do in the next talk is to show you how for permutation groups one can build a clever data structure which uses orbits and stabilizers for a set of stabilizers stabilizing more and more points, looking at orbits on each level, how one can use that to build a data structure which can, for example, calculate the order of the group, allows to decompose group elements into generators, and that's the basic data structure which underlies permutation groups. Yeah, but more about this next time. Thank you very much.